Hi everybody. This is the lecture on section 6.4, which is on the Graham-Schmidt process. And as far as, and this is the last section that we'll be covering in the course. Okay, so the Graham-Schmidt process is as follows. Let W1, so here is the process, let W1 to Wm be a basis for subspace W of Rn. Okay, typically not the whole of Rn. Okay, you'll see why in a moment. You know, it's some proper subspace. Let V1. So you know what I'm going to do? I'm going to write V1 like this, but then I'm gonna skip the hats on the vectors in order to be just a little neater. So I'll put a few in, but then I'll start leaving them out. Let V1 just equal W1, just some sort of trivial thing here, trivial designation. And now just V1 by itself is an orthogonal basis for span W1. Obviously, I mean, it's just the same vector. And of course, it's an orthogonal basis because, well, there's no pair of vectors to be orthogonal with. So it's sort of vacuously orthogonal. Okay, so that's where the process starts. Okay, it gets better. Let me see, I give myself enough space. Well, let's leave it like that. All right. Let V2 be equal to W2 minus W2 dot V1 over V1 dot V1 times V1 times vector V1, right? And now let me see, can I, oops. And now V1, V2 is an orthogonal basis for span W1, W2. Let V3 be equal to W3 minus W3 dot V1 over V1 dot V1 times V1 minus W3 dot V2 over V2 times V dot V2 times V2. And now V1, V2, V3, V1, V2, V3 is a basis for the span of W1, W2, W3. Try one more step. Let V4 equal W4 minus, okay, W4 dot V1 over V1 dot V1 times V1 minus W4 dot V2 over V2 dot V2 times V2 minus W4 dot V1 over, or V3 over V3 dot V3 times V3. And now V1, V2, V3, V4 is an orthogonal basis for the span of W1 through W4. And it just keeps going like that. And you keep going till you're done. W1, W2, W3, W4. Okay, and it just keeps going like that until you've used up all of the W vectors. And you've got a basis for the whole subspace of W. So in the end, you've got Vm equal to Wm minus Vm dot V1 over V1 dot V1 times V1 minus Vm dot V2 over V2 dot V2 times V2 minus blah 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 Vm minus 1 dot V I think I messed something up. Wm dot V1, V1 dot V1, Wm dot V2, V2 dot V2, Wm dot Vm minus 1 over Vm minus 1 dot Vm minus 1, Vm minus 1. And now, V1 to Vm is an orthogonal basis for the span of all the vectors, which is just that subspace W. Okay, so you just keep moving the process like this. Let's do a proof of this. Not for general m, but let's just do, say, m equal to 3, just so you can kind of see how it goes. Because it is kind of interesting in how it works out. Okay, so proof. So we'll just assume that m is equal to 3 in order to avoid details. Using mathematical induction. Which is a tool that you would need to actually do a proof for general m's. Okay, so first of all, notice that, okay, V1 is W1. So V1 is a linear combination. Well, so span V1 is equal to span W1. V2 is equal to, well, what was it? A linear combination of W1 and W2. All right, V2 was a linear combination of W1 and W2. It's right here. V2 is W2 minus this V1, but V1 is W1. So it's a linear combination of W1 and W2. So a linear combination of W1 and W2 is a linear combination of W1 and W2, and vice versa. Linear combination of V1 and V2 is a linear combination of, or linear combination of W1 and W2 can be written as a linear combination of V1 and V2. V3 is equal to a linear combination of W1, W2, W3. So span W1, W2, W3 is equal to span V1, V2, V3. Right, because what's V3? It's right here. V3 is W3 plus, that's V1. This times V1, but V1 is W1. Minus this times V2, but V2 is a combination of W1 and W2. So V3 is just a linear combination of W1, 2, and 3. So a linear combination of V1, V2, V3, or W1, 2, I do it backwards. V1, V2, V3 is just a linear combination of W1, W2, W3 and vice versa. A linear combination of W1, 2, and 3 can be written as a linear combination of V1, 2, and 3, etc. It keeps going like that. V4 is a linear combination of W1, 2, 3, and 4. Right, and it keeps going. So the spans are always the same. Now we just have to show orthogonality. So all that is left is to show that V1, V2, V3 are orthogonal. Okay? So let's write down those three vectors, V1, 2, and 3. Oops. Alright, so we just need to check orthogonality of these three vectors. So there's three pairs of vectors to look at. V1.V2, V1.V3, and you got to do them in this order. V1.V2, V1.V3, V2.V3, or maybe we should do 4. Let's assume m is equal to 4. It'll look a lot nicer that way. Oops. Okay, so let's check that out. So just checking that they're orthogonal. Okay, V1 dot V2 is equal to what? Well, it's W1 dot W2 minus this constant times W1 dot V1. And the V1, well, we'll write it as V1. It's V1 dot W2, V1 dot V1 times this constant, right? So it is W2 dot V1 using distribution. All right, V1 times V2, V1 dot V2 is V1 dot W2 minus this constant times V1 dot V1 minus that constant W2 dot V1 over V1 dot V1 times V1 dot V1. These cancel, and I got W2 dot V1 minus W2 dot V1. That's 0. V1 dot V3. V1 dot V3. So that's V1 dot W3. Right, V1 dot, so we're distributing. V1 dot W3 minus this constant, well, W3 dot V1 over V1 dot V1 times V1 times V1, or dot V1, minus V1 times V2, or V1 dot V2, but that's 0. We already know it's 0. Alright, so V1 dot this minus V1 dot this minus V1 dot this. Alright, but V1 dot V2 we already know is 0. We checked it, so that's why you got to do it in order. So what do you get? V1 dot V1 cancel, and you get V3 dot V1, or W3 dot V1 minus W3 dot V1. That's 0. V1 dot V4. So it's W4 dot V1 minus W4 dot V1 over V1 dot V1 dot V1. Right? Dot product with this one is 0. V1 dot V2 is 0. We already determined that. And then V1 dot V3 is 0. We already determined that. So you see why you have to go in order like this. I mean, it matters how you check them, because you have to establish this is 0 and that's 0 before that's 0. These guys cancel, and that's V4 dot V1 minus V4 dot V1 is 0. All right. V2 dot V3. V2 dot V3. Well, that's V2 dot W3. Right. V2 dot W3. V2 dot V1 times a constant. That's 0. Right? V2 dot V1 is 0. Minus V2 dot V2 times this. W3 dot V2 over V2 dot V2 times V2 dot V2. But these guys cancel and these subtract, give you 0. Nice. V2 dot V4. So W4 dot V2 minus V2 dot V1, 0. Minus W4 dot V2 over V2 dot V2 times V2 dot V2 minus V2 dot V3, 0. These guys cancel and we get 0. Right, and now V3 dot V4. Well, that's V3 dot V3 dot W4 minus V3 dot V1. V3 dot V1 is 0. V3 times V2. V3 times V2, but V3 times V2 is 0. And then V3 dot V3 times this. W4 dot V3 over V3 dot V3 times V3 dot V3. Cancel and you get 0. There it is. Pretty neat. So it just goes on and on like that. goes on like that. So that's the proof for m equal to 4. So let's take an example. Let's do an example. So consider the span W1 equal to 1, 1, negative 1, 0. W2 equal to 1, 1, 0, 1. And W3 equal to 1, 1, 0, 0. Okay. So find an orthogonal basis for W being the span of W1, W2, W3. Okay, and these guys are already linearly independent. You know, you can check it, but they are, okay? So we apply Gram-Schmidt. So V1 is equal to W1 is equal to 1, 1, negative 1, 0. V2 is W2 minus W2 dot V1 over V1 dot V1 times V1, which is 1, 1, negative 1, 0. And, let's write it. Let's write W2 here, so we've got, that's fine, W2 minus W2 dot V1 over V1 dot V1 times V1. So W2 is this one, 1, 1, 0, 1, minus, okay, W2 dot V1, so the dot product of these two. W2 dot V1 is, well, 1, 2, 0, 0. So 2 over V1 dot V1, which is 3, times V1. 1, 1, negative 1, 0. So we get 1 minus 2/3, that's 1/3. 1 minus 2/3, so that's 1/3. 0 minus minus 2/3, that's positive 2/3. And then 1 minus 0 is 1. Okay, so 1/3, 1/3, 2/3, 1. Notice that, okay, V1 dot V2, okay, is equal to, well, it's 1 times 1/3 plus 1 times 1/3 minus 1 times 2/3, which is 0. So they're orthogonal. V3, okay, so this is V2, and V1 dot V2 is 0. So now V3 is W3 minus W3 dot V1 over V1 dot V1 times V1 minus W3 dot V2 over V2 dot V2 times V2. So this is equal to W3 is 1, 1, 0, 0. Minus W3 dot V1. So here, here's W3, here's V1. The dot product is 2. Over V1 dot V1, that's 3 times V1. 1, 1, negative 1, 0. Minus W3, which is this vector right here, dot V2, which is this vector right there. Right, this vector dot this vector is 2/3 divided by this one dot itself, V2 dot V2. So that's 1/9 plus 1/9 plus 4/9 plus 1. So it's 6/9 plus 1, which is 15/9, which is 5/3. So 5/3, these threes cancel, times this vector. 1/3, 1/3, 2/3, 1. So this is equal to, so we've got 1, 1, 0, 0, minus 2/3, 2/3, minus 2/3, 0, minus is 2/5. Right, so 2/5 times 1/3, that's 2/15. 2/15. 2/5 times 2/3 is 4/15. And then just 2/5. So what do we have in the end there? So this is the vector. 1 minus 2/3 is 1/3 minus 2/15. Right, so that's 5/15 minus 2/15 is 3/15. 1 minus 2/3 minus 2/15, same thing, 3/15. 2/3 minus 4/15, so that's 10/15 minus 4, so that's 6/15. So divided by 3, so that's 2/5. Right? 10 minus 4 is 6. And then the last one is just minus 2/5. So now we just have to check those dot products, right? We already checked that V1 dot V2 is 0. So now let's check the rest. So V1 dot V3 is equal to, right? So this is V1, this is V3. So the dot product is 3/15 plus 3/15 minus 2/15, or 2/5. So that's 6/15, and that's 6/15 is 0. And then V2 dot V3 is going to be equal to, so, 1/3 times 3/15, that's 1/15. 1/3 times 3/15, that's 1/15. 2/3 times 2/5, that's 4/15. And then minus 2/5. So that is 6/15 minus 6/15. That's 0. Right? So these will check out. So that's an orthogonal basis for W. Now, as you notice, there's quite a bit of really kind of, heavy-duty arithmetic going on here. It's more easily done by a computer. But if you pick a different ordering for that basis, the calculation might become easier. All right, so this is an orthogonal basis. So this is an orthogonal basis for W. Let's do the same example again, but let's order the vectors differently. Okay, so here's those same vectors. Okay, so again, span W is the span of W1, W2, W3. Find an orthogonal basis but with the new numbering shown. For W1, W2, W3. So same vectors, but I want to call that W1. And then this will be W3. Okay, we'll call this one W1. This one will be W3, and we'll leave that one as W2. Okay, so V1 is W1, 1, 1, 0, 0. Now V2 is W2 minus W2.V1 over V1.V1 times V1. So this is equal to W2, 1, 1, 0, 1 minus W2.V1 is just 2. 1 plus 1 plus 0 plus 0. So that's 2. Over V2.V2, or sorry, V1.V1, which is again 2, times V1. Right, so that's just this minus that. So it's 0, 0, 0, 1. A lot easier this time around. V3 is W3 minus W3.V1 over V1.V1 times V1 minus W3.V2 over V2.V2 times V2. So this is equal to W3 was 1, 1, negative 1, 0, like so, minus, so this is W3, W3.V1. W3.V1, that's W3, that's V1. The dot product is 2. Over V1.V1 is 2. Minus V1, 1, 1, 0, 0. Minus W3.V2. Right, here's W3, here's V2. W3, V2, dot product is 0. So we just get 0, 0, minus 1, 0. Okay, so our orthogonal basis for W is 1, 1, 0, 0, 0, 0, 0, 1. I mean, it's almost an elementary basis. And that's it. So, I mean, depending on which vector you pick first, things can be a lot easier. Essentially, usually, picking the vector with the most zeros in it to go first, and the next number of zeros to go next, picking more zeros at the beginning is helpful. Right, because when there's not a lot of zeros in here, the number in the denominator of that fraction, right, like V1.V1 can get really big. Because when you take a vector dot product with itself, 1/3, 1/3, 1, -1, or something like that. I mean, what does it become? It becomes 2/3 plus 2, which is equal to 8/3, right? I mean, and the more fractiony you get inside here, the worse this thing is going to become. So when you have vectors with more zeros in them, pick those first for the Gram-Schmidt process. Okay? All right, that is the lecture for this section, and that is the end of the course.